started. What do you want to look at first?
The free body diagram.
Okay, you want to look at that question? Okay, so you will have a question like this. It'll be an object. It'll be an object that will have some force acting on it. It'll be moving across a certain distance. Let's say that the distance is 2 meters. Let's say that the object is, I don't know, 3 kilograms, and it'll have a force that's acting up in this direction. It's like somebody's pulling it, right? And I'll ask a couple of things. Let's say this force is, I don't know, 20 newtons, sort of making up numbers. And then I'll give you a coefficient of kinetic friction. Say it's 0.1. And I'll ask you a couple of things. I'll ask you first, what is the kinetic friction or the normal force or something along those lines? You actually have to find all those things to figure out what is the total work. And the total work is really what I'm looking for here. Yeah, I know this is still sort of chapter 4, but I just want to have one last punch at chapter 4 to make sure that you're getting 2D forces. Okay? But it's still related to our work and energy. So the way that you do this is you do what we did in chapter 4. That's where you're labeling all of your forces. You have your kinetic frictional force. You have your weight. You have your normal force. And then you have this extra force, which is F. And so I'll call this F cosine. Let's say this angle is 30 degrees. Cosine of 30 degrees. This is F sine of 30. And so those are our resolved vectors on our coordinate system. Those are all the forces, and it's going to be the same problem. So you just have to learn how to do this one. If you don't get 2D forces, that's not really okay, but just do this tomorrow and you'll be okay. All right? I'll ask you a couple questions. I'll ask you, what is FK? I'll ask you, or I'll ask you, what is the normal force? I might ask you, what is the work done by F, or FK, or the total work done? And let's just answer all these questions right now. So you'll have to find Fn first. And the way that you find Fn is that you look at these forces in the y direction. Because I know that the sum of the forces in the y direction has to equal to 0. That's always true because it's not moving in the y direction. And so I can say F sine 30 minus Fn, plus Fn minus Fw, that's equal to 0. So Fn will be equal to Fw minus F sine 30. And so that's going to be Fw is 30 newtons minus 20 sine of 30. And so you can find that. It's 10, right? Yep. 30 minus 10 is 20 newtons. So that's my normal force. That could be one of the questions I'd ask you. Or another very similar question is, what is Fk? Which is easy once you know Fn, because it's just mu k times Fn, which is going to be, in this case, mu k was 0.1 times 20, which is 2 newtons. You have to do that anyway. So all this up to this point, you're going to have to do regardless of what I ask you, because you'll need to find the normal force, you'll need to find the kinetic friction. Now, the next part is to find the work. And let's say the displacement here is 2 meters. So if I want to know the work done by F, the work done by F is going to be equal to the component of the force in the x direction. That's F cosine of 30 times the distance, which is, what was it? 2 meters. Times 2 meters. So that's 20 cosine of 30 times 2 meters. Okay, I trust you. I just almost done. Yeah, so 34 or 35. We'll just call it 35 joules. So that's the work done by F. Not the whole force. The whole force doesn't do work. There's a component of that force, this component right here, that does no work at all. I could also ask you, what is the work done by Fk? And the work done by Fk is going to be Fk times d, or 2 newtons times 2 meters, which is equal to 4 joules. But it's what? Positive or negative? It's negative. So I'm going to put a negative on there just because frictional forces do negative work. And that force is opposite the displacement. Really what I'm doing there is I'm doing a cosine of 180. I didn't write that in there, but really I'm doing 2 newtons times 2 meters times cosine of 180. And that cosine of 180 is negative 1. Or I could ask you, what is the total work? Goodness bless you, Anija. The total work would be 35 minus 4, or 31 joules. That's probably the more likely question that I'll ask, but it requires doing all those steps up to that point. That is the question I'm going to ask. What is the total work that you'll do? But it requires finding the work done by F, the work done by Fk, it requires you to find Fn, like all those things. This entire problem you have to be able to work through. I know that seems like a lot, but it's stuff that we've done before. It's stuff that you've already seen on the Chapter 4 exam, and you know, not hiding anything. You're going to have to do it tomorrow, so make sure that you practice that. There are some example problems on the old exam, so go back and look at those. Make sure that you can do that. Yes, you can, right? Yes, you can. Okay? Good, please. Remind you of the other free response. You're going to have one of these type problems where I ask you, say, what is the speed here, or what is the height that it goes to, a roller coaster type problem, conservation of energy. Be careful, where students often mess up is right here. They always assume that it only has potential energy, but if it's moving, it also has kinetic energy. So just take a big deep breath as soon as you see the problem, and then go through and say, okay, what does it have here, potential or kinetic or both? And make sure you're looking at H. If H is 0, that means no potential energy. And look at V. If V is 0, that means no kinetic energy. The other problem that you'll have is a collision problem. I'll have a figure that'll look something like that. If it's a collision, is that an elastic or inelastic thing? It's what? You're right, inelastic. If they're touching, that's inelastic because they're losing energy. So it'll be an inelastic collision. If they touch and stick together, that's a perfectly inelastic. They both only conserve momentum. So you have one of those. We can look at one later if you want. And then the third will be a kinematics problem. That's where you're using these equations. Theta equals omega naught t plus 1/2 alpha t squared. And omega equals omega naught plus alpha t. I find the hardest part for students is just knowing what these variables are. That theta is equal to our displacement, omega is equal to our angular velocity, and alpha is equal to our acceleration. Because back on the exam 1, you had similar problems. In fact, you had more complicated problems than the ones you'll see here today, except we were dealing with, X, V, and A. And somehow when you throw Greek letters in there, it just throws everybody off, okay? But they're just theta, omega, and alpha. So get used to it. Greek letters are cool. Anija?
So theta is always going to be like an angle?
Theta will always be an angle, right? And omega will always be an angle per time. And alpha will always be an angle per time squared.
For like meters, that's when you do S equals theta.
That's right. Yeah, so if you're ever asking for a distance in meters and you're dealing with rotational quantities, that means that you're dealing with these equations where I'm relating my angular quantities to my linear quantities. S equals theta r, V equals omega r, and A equals alpha r. And remember on these, when you're dealing with the angular quantities, they must be in units of radians. That's one of those situations where your units have to be in radians. You never go wrong with radians, but in this case, if you're not in radians, you will go wrong. Okay? Just in general, y'all should know this about me by now, but if I ever, in the problem, say something about the units, express your answer in so-and-so units, then that's important. You're going to have to do something with that. So make sure that you're on the lookout for that. I don't say that for no reason. In fact, usually every word is important. So if I say something, it's probably important. I'm trying to clue you into something that you're going to have to do, and if you don't do it, you're going to get the wrong answer. I'm not a bad guy. Like, I'm kind of nice sometimes when I'm writing test questions. I try to make things very clear to you. So watch the language. Integer?
Are you going to have one of those questions where we have to figure out two variables?
I'm not going to have you solve a system of two equations. No. But you will have a problem where you have two unknowns. But it'll be a different equation to figure out. Right. Yeah. Okay? But no, if you think you have to solve a system, two equations with two unknowns in each equation, no, you're not going to do that. Okay. What do you want to look at first?
Yeah, rotational kinematics.
Rotational? All right, let me pull up some old exams, and we'll sort of go through those first, and then we can go back and look at exam 3. Go back look at 3 of fall 18. Is that okay? So these are usually at the end. Oh, wait, no, this would be exam 4, fall 18. Oh, boy. Okay. So, this is fall 18, exam 4. Number 6 is sort of a basic kinematics problem. Even though you're going to have kinematics problem in your free response, you'll probably also have it in your multiple choice too. They'll just be simpler one-step problems. So let's look at number 6 first. Thing with the kinematics equations, you can use revolutions. You need a revelation too, right? You can use revolutions or radians or degrees or whatever. It doesn't matter what you use in those equations. So let's look at number 6. A fan spins at 12 revolutions per second. The way I like to work these is I just write down everything that I know. We did this in chapter 2 as well. So I have omega naught equals 12. You turn it off, and it slows at 3 revolutions per second squared. So alpha is 3 revolutions per second squared. Now, I got to be careful. See, I put that word slows, and so I know that if it's slowing down, the acceleration is opposite the direction of the velocity. So that tells me this is negative. That's what that slows is. What is its angular displacement before coming to rest? Theta. I want to know theta. And before coming to rest, that is omega is equal to 0. So notice this is a little bit different than problems we've worked before because omega naught is usually 0 and omega final is usually not 0 because usually we're speeding up, but here we're slowing down. But you still work it the same way. So if I want to know theta, if I ever need to find theta, I know that this is omega naught t plus 1/2 alpha t squared. So I always start with that. And then I ask myself, okay, what are my unknowns here? I don't know theta, and I don't know t. So what I would do is I need to find t. That's my first order of business. This is a great example, by the way, of your free response question in kinematics. It'll be a 2-step question like this where you have to find something else. So to find t, which is my first order, Well, I know I can't find it with this, so I only have two equations. I must be having to use this. And it turns out that my unknowns here are just t. I know omega naught, and I know alpha. So I say omega, which is 0, equals 12 minus 3 times t. So t is equal to 4 seconds. And now that I know 4 seconds is t, I can plug that in over here. I'll do that right here. That's 12 times 4 plus 1/2 of negative 3 times 4 squared. That's equal to 48 minus 1.5 times 16. Is that 24? Minus 24. So it's 24 revolutions. All right, so the answer is A there. Good example of a free response. In your multiple choice, you have kinematics too, but they'll be simpler one-step problems, kind of like this question where I just asked, what is the time? Okay, let's do another one. I told you, hey, look at number 5. Remember I told you there'd be a question like number 5, so let's work number 5 here. This is the Ferris wheel, and I want to know the normal force acting on the object. First, any questions on this one? We cool on that one? You gonna get that one right tomorrow? Everybody? Are you gonna get it right?
Yes.
Okay.
On the equation sheet that has theta equals theta naught, like those we all do we need to know like it like that.
No, theta naught is always 0, as far as you're concerned. Sometimes there are situations where you don't want theta naught to be 0, but as far as you all are concerned, theta naught will always be 0.
Yesterday was throwing me off because like it had I looked at the equation sheet and it had that part in it. I was like, okay, I don't know what this is.
I know. It's always 0 as far as we're concerned. Okay. Number 5. Let's look at number 5. That's one of our. It'll be a multiple choice question. It could be a Ferris wheel, or it could be a guy twirling a string, right? Like we did in class. But nonetheless, something that's moving in a circular path that is vertical, not horizontal. Horizontal is different. It's a lot simpler when it's horizontal. I'll zoom in. Can y'all read that now? I saw you all squinting. You were squinting, trying to read it. I've had to start wearing glasses. Like I have reading glasses and I have driving glasses. And I've never had to wear glasses my entire life. Never worn glasses. Like a lot of you either wear glasses or contacts. Me, I've had like perfect vision for my entire life. But then when I hit 40, that presbyopia, which is like old people vision, it starts to go. And I don't like wearing glasses. And I had this student come in. That student's not here. But a student came in and they had printed their old exams 4 pages to 1 sheet of paper. And she brought it in. I'm like, what do you expect me to do with this? I'm pulling out a magnifying glass and trying to read it. Anyway, so a Ferris wheel, there's the radius. It's rotating at a certain speed. And look, I even converted it for you. What a nice guy, right? And a person with a mass sits in a chair. As the Ferris wheel spins, the person is at the lowest point. What is the normal force acting on the person? First of all, if this person's 100 kilograms and he's sitting in a chair, what would the normal force be? He has a weight of 1,000 newtons. What would his normal force be? Just sitting around. That would be equal to his weight, right? At the bottom of this Ferris wheel, is the normal force going to be more or less than 1,000 at the bottom? More, right. And so that means I can get rid of this. I can get rid of this. And honestly, C, that's kind of big. I could probably get rid of C. Like C just, I'm going to get rid of C just because I don't think it's right. It seems really big. So it's either A or E. That helps me a lot. Now I'm down to sort of 50-50. Like you could just not work this problem, guess, and maybe you'd even get it right. But at the bottom, what we need to consider are a couple of things. First, what are the forces? I have my normal force here. I have my weight here. And then what is the direction of my centripetal acceleration? That direction, it's always towards the center of the circle. Right, it's up in this case. And then I do the sum of the forces equals m times a. And because this is up, it's positive. So I'm going to do a positive a. If it were down, it would be negative. So if I were up at the top of the trajectory, my acceleration would be a negative a. And I would have a negative right there. The sum of the forces is Fn minus Fw. That's equal to mass times my positive acceleration. This is our centripetal acceleration. I'm looking for the normal force. So my normal force is equal to Fw plus m times ar, which is my centripetal acceleration. Remember that ar, it's not g, right? That's not their acceleration. Their acceleration is v squared over r. That's their centripetal acceleration. So this is going to be m times g, that's Fw, plus m times v squared over r. M is 100, so that's 1,000 newtons for the first one, plus 100 times v squared. Oh, I don't have v. But remember, I had two expressions for centripetal force. I had this, and then I also had m omega squared r. That might even be on your equation sheet. I'm not sure. Is it? No. Okay, it's not. But you can get it just by substituting v equals omega r in for v, and you get this alternate expression. If you don't want to worry with that, then you can take your velocity, your omega, which I gave you in the problem. Omega was 0.1 radians per second, and just convert it into a velocity by multiplying by the radius, which is 20. You follow what I'm saying there? That if I don't want to worry about this extra equation, I can just change my omega, which is 0.1, into v by saying omega times r. Notice that it's really important that omega be in radians when you're working with this equation. It's really just when you're doing the kinematics equations that it doesn't matter, but every other instance of using omega or alpha or theta, it has to be in radians. It's only those two kinematics equations where it doesn't matter. And that's just because your units, they all cancel out, or they carry through to give you the answer in the same units. But here it must be in radians. Okay, am I going to go through and make answers that aren't in radians and put them as one of the options? Of course, because I'm a nice guy, and I want to make sure that you understand the content. Okay? All right. So I'm going to do it this way. Omega is 0.1 squared times r, which is 20, and then that'll give us the right answer. 1,020. Right? Yeah. Yeah, that's right. 1,020. Okay? You'll have that question on there. It'll be something very, very similar to that. Let's look at some more of these. Oh, I didn't square it. Oh, you didn't square it. You got to square it. You don't know how to do this number 3? What is the angular displacement of a clock's hour hand in radians between noon and 6 p.m.? Do y'all know how to read an analog clock? Do you? Do you really? Between noon and 6 p.m., how many degrees does the hour hand travel? 180 degrees. Okay. How many radians? Pi. Okay, good. So I have, if I want to know the angular displacement, well, this is just going to be pi. If I want to know the angular velocity, what would that be? Well, My angular velocity omega is delta theta over delta t. It goes through pi radians. And what's my delta t between noon and 6 p.m., the hour hand? 6 hours, yeah. So that would be 6 hours. Depending on the units, I might have to do some unit conversions, but that's how you do it. Okay? I like the clock questions. If you look back at old tests, you often see some variant of it. Some of it's second hand, some of it's hour hand, some of it's noon to 6, noon to 3, different, or maybe all the way around. Okay? So make sure you look at that because you'll probably see something similar regarding the clock question. Let's look at some other exams. Can we, what was that, fall 18? Let's look at fall 17. Rotation still? Want to look at more rotation? Or want to look at other stuff? All right, we can come back to it. So let's look at the other stuff. Is that okay? All right. Okay, this is like the roller coaster, the bug. I know it's a little bit different context, but it's really the same type of problem. So in this problem, this fall 17, exam 3, number 1, I have a bug that has kinetic energy and potential energy at the beginning. The reason I know is because he has a height and he has a velocity at the very beginning. And I want to know what is his speed at the bottom of the ball. And I know at the bottom of the ball he only has kinetic energy. So I would say EI equals EF. Kinetic energy is 1/2 mv squared plus potential energy is mgh equals 1/2 mv squared. M's all cancel. I have the mass here, but in general, if you don't have the mass and you think that you need it, just keep going because at some point the mass will probably cancel out. Don't freak out if you come to a problem and you think you need the mass because you need to figure out something, but then just keep going. Just sort of keep your equation moving, and then you'll see a little bit later that the mass will cancel out. Okay? We've done that a lot on this, but that's true for other questions too. In fact, there is a question on the test tomorrow where at first it seems like you need the mass, but then just one little step, and then you find that it all cancels out. Okay, so 1/2 of 1 squared, that's the velocity, plus 10 times 0.4, that's the height, equals 1/2 of v squared. So that's 0.5 plus 4 times 2 equals v squared. So v is equal to square root of 9, or 3 meters per second. Okay? That'll be, you'll have a problem on the free response that will be related to that. Each free response, you have 4 questions. Each will have 2 sub-questions. Okay? That's 8 questions. That's like a good fraction of your test. Any of these standing out to you? You want to look at? Number 2, 3, 4. Yeah, love to. Like in the free response at first? Okay. Let's do this number 14. What is the final velocity of the 2 kilogram ball? Very similar to what you'll have tomorrow. You'll have a figure that looks a lot like this. You just have different numbers, maybe different directions. But the way that you work it will be the same. I'll say PI is equal to PF. These are vector quantities, so you have to be really careful with your signs. So the first one is 1, remember P is equal to M times V. So I have 1 kilogram times positive 3. In fact, I think it's good practice to just write either positive or negative on all of your quantities, because then it makes you think about them. So we tend to default to positive, but I like just writing signs on all of them. Plus 2 times negative 4 is equal to 1 times negative 1 plus 2 times VF. You might be inclined to think that VF is going to be to the right, but that's not always the case. Like we might be inclined to think, well, if they're coming this direction, they bounce off, then they must bounce off in the same direction. But I think in this case, that's actually not true, that they both wind up going to the left. But let's see. Just don't go into the problem with that already in your mind. So 3 minus 8, that's negative 5, plus 1 equals 2 VF. So that is negative 2 meters per second, or 2 meters per second to the left. So this guy would be going in that direction with 2 meters per second. I know it's to the left because it's negative. It's a free response question. I'll have 2 questions. I'll probably ask you some conceptual question regarding that. Okay? As well as a calculation question. Remember, it's not 2-dimensional. It'll be a 1-dimensional momentum problem. Clear? Good. Everybody should get that one right. You'll have some momentum problems in the rest of the exam too. Like number 16, for example. We've had variations of this. I have a cart with a mass of 20 kilograms and it's traveling to the right at 12 meters per second. And then I drop a mound of trash onto the cart. And now the trash has a mass of 10 kilograms. This is a perfectly inelastic collision. I have 2 objects that come together and they move off at the same velocity. So the way I'd work this is I'd say PI is equal to PF. Initially, it's just the mass that has momentum, 20 kilograms times 12 meters per second. And then that's going to equal to the combined mass, 20 plus 10, times VF. Okay, so that's going to be 240 divided by 30 equals VF, or 8 meters per second. I'm pretty sure that I have a collision problem that doesn't have a figure. I like to do that just so that you can read the problem and then translate that into some physical scenario. That's often much more difficult. If I give you a figure, I've already done a lot of the work for you. But being able to read something like this and then translate that scenario into an equation is not easy. It's a skill that a lot of people don't have. And that's a skill that I want you to have. Okay? All right. Number 17, you'll have something like that, where you have to find the force or the impulse or something like that. You'll know this problem because it'll have a time in it. You'll know that it's a problem that is related to this, delta P over delta T. And the time should sort of key you off on that. By the way, you should be fairly clear on how my exams work by now, that you should come into the exam knowing that it's going to come in order. So your work and energy problems are going to be the first page or 2. Your momentum problems are going to be the next page or 2. Your rotation problems will be the next page or 2. And then the torque problems will be the next page or 2. That's 8 pages. But it won't be that long. It's like 4 pages. Okay? That's like a Dr. P exam, isn't it? Y'all had Dr. P? You had Dr. P for organic? For lab? I hear that his exams are like books. A lot of questions. Does he have a lot of questions?
Yes.
Yeah, I love that man. Hey. Okay, so the big part of this is finding the right sign, making sure that you get your signs right. And I always like to draw a picture. I have an object. There's my VI. It bounces, and then my VF is in this direction. And so my VI is 4.8, but it's negative 4.8. and my VF is 3.2, but it's positive 3.2. Okay, so this is going to be M times VF minus VI divided by delta T. So my mass is 0.3 kilograms. That's right here. VF minus VI, that's 3.2 minus negative 4.8 divided by delta T, which is 0.03 seconds. What's that? 8, 2.4, 0.3. Is it 80? I think it's 80. All right, so the answer is 80. Almost always, basically always, you're going to be adding these two numbers, not subtracting them. You're taking the difference in them, but one of them is going to be an opposite sign. So always, as far as we're concerned, this is going to be a sum, not a difference, even though the equation has a difference, because they're in opposite directions. That doesn't mean like always in the world. One day you might come into a situation where VF and VI are in the same direction, but then you'll have to deal with that, with or without me. Okay? Let's look at others. If you have any requests, I'm willing to do that. We did work, we did energy. We didn't do, let's do, sorry, somebody said something? Torque. Oh yeah, we didn't do torque. That's not on this exam. I'm going to go to exam 4 for fall 17. Yeah, be careful because sometimes torque gets buried in exams, just sort of the way that we do chapter 8. But like number 7, you'll have 2 questions regarding chapter 8. One of them will be a question like this. I'll give you a bar, and I'll ask you what is the net torque on it. The other question will be kind of like a lever problem or a seesaw problem, where I ask you what is the force required to balance this. 2 questions. I've already told you more than half the exam. So you should be able to get all those questions perfectly right. Right? Yes. Yes. Shouldn't even have to grade them. Yeah. Okay, so consider this figure of a rod rotating. I want to note where is the axis of rotation, first of all. That one. And then I want to go through and ask myself, which of these forces don't provide any torque? And this one doesn't provide any torque because R is equal to 0. Remember, torque is equal to FR sine theta. And there are 2 ways that a torque can be 0. One is that the R can be 0, and 2, theta can be 0 degrees. And if theta is 0 degrees, the sine of 0 is 0. And so this first, the 10 Newton force, or this one, doesn't provide any torque because R is equal to 0. Is there another force that doesn't provide any torque? Right. This one has theta equal to 0 degrees, so the torque is also 0. So this one's a really easy problem because there's only one force that causes a torque, and it's not even off axis. Like it's perpendicular. The angle theta is 90 degrees. And so this torque is FR sine theta, which is 10 newtons times 1 meter times the sine of 90, which is 1. And so it's just 10 Newton meters. It is clockwise. That means that it's going, this force causes a motion, a rotation in that direction, which is clockwise. Let's do another one that is not so simple, because it could be a more complicated one. I'll just make one up. Let's say that my axis of rotation is right here. Let's say that I have a force here. I have a force here at an angle of 30 degrees. We'll say that this is 3 newtons. Say this is 4 meters. This is 0.5 meters. And then let's say that there is a force right here of 2 newtons. And this is 1 meter. Okay, oh, I didn't give you this force. Let's say this is 1 newton. But it doesn't matter, right? Because this force provides no torque. You wait, like you have a door. If I push here, there's no torque. Or if I push here along the axis of the door, then that doesn't provide any torque either. Okay? So here, my angle theta is 0, or here my angle theta is 0, so no torque. But the other do provide torques. I need to identify, are they positive or negative torques? This is a negative torque. This is also a negative torque. So when I add them up, I'll have both negative numbers. You need to identify the sign of the torque, because then when you add them up, if one's positive and one's negative, then you'll be taking a difference between those two. The net torque then is going to be 3 newtons times this distance. You might have to do a little figuring on that, but that distance would be 3.5 meters. 4 minus a half times the sine of 30. That's negative minus 2 newtons times 1 meter times the sine of 90, which is just 1. And then the sum of those two numbers would be the net torque. So you'll have a problem like that. You'll also have a problem that is just like you did in lab with the meter stick, where you're finding the balanced mass or forces, where I'll give you some lever, say looks like this. Say I have a force here of 10 newtons at 2 meters, and I want to know what force down here at a distance of 6 meters is the balancing. I just set them equal to one another. I say 10 times 2 has to equal to the new force times 6. And that force would be 20 divided by 6. Or 0.03? No, 3.3. Is that right? Yeah. Yeah. Mm-hmm. Those are your 2 torque problems.
How come on this chart,
Yeah.
the values are negative for the voltage right here? And one down there.
Yeah, this one was negative, but the negative is in clockwise. Good. All right, clockwise is negative, and counterclockwise is positive.
You can put a negative in the problems.
Taylor?
So you just know that displacement to the left is 0.5 because it is on the other side at the top. So like when you're finding R for the negative torque, -3 and times 2.5.
How did I know this was 3.5?
Like is because like 0.5
Yeah,
is
right.
like
Yeah, so yeah, I know this total distance is 4, and this is 0.5. That means this distance has to be 3.5. Yeah. You'll probably have to do something like that on the exam. Like I won't give you the distance right off, but you have to be able to read the diagram. That's an important skill too for, I don't know, if you ever have kids or whatever, you have to put together a bike or whatever, right? You have to be able to read those diagrams. Okay? What else y'all want to do? You want to do more?
There was one with a slide that had like static It was friction.
This one, like number 2. There are variations on this on a lot of exams. Let's look at this. This is Fall 17, Exam 3. Kid comes down a slide. Slide is 2 meters high and 4 meters long. What that means is that this is 2 meters and this distance is 4 meters. And it has a frictional force of 5 newtons that acts along the entire length of the slide. How fast is the kid when he reaches the bottom? So here's the kid. He's a blocky kid. People made fun of him when he was a kid. So up here he has potential energy. Down at the bottom he only has kinetic energy. Now if there was no friction, it would be mgh equals 1/2 mv squared. And we could figure out his speed. You don't have to write this down, but you could say g times 20, g times 2 equals 1/2 v squared. And so v would be the square root of 40. Or 6.3. But I know that there's a frictional force acting, and so he's going to be traveling faster or slower than that? Slower. Oh, so boom. Like I can just get the answer right there. The answer has to be 6. But the way that I would calculate that is that the work done by friction is equal to F times D, and that work takes energy away from that kid as he slides down the slide. So whatever potential energy he has at the top, minus the work done by friction, F times D, is equal to 1/2 mv squared. So I would say mgh 10, 10, 2 minus 5 times 2, 5 times 4. I multiplied the force times the distance over which the force acts is equal to 1/2 of 10 times v squared. 200 minus 20, 180 divided by 5. That must be 6. Yeah. Okay. I asked that question a lot. I'm sorry. Was that too fast? I don't know if I can bring it back. I'm sorry, it's gone forever. What else you want to look at? Let's look at number 10. You increase the energy of an object 200 joules by pushing on it with a force F. If you push on the object over a distance of 4 meters, what is the force F? Well, this is just work energy, right? Work is equal to a change in energy. But work is force times displacement. That's a change in energy. So this is just F times 4 equals to 200. And so F has to be 50. See? Not hard. Once you start thinking about it in terms of our various principles, the conservation of energy, the work energy theorem, Newton's second law, that's the F equals delta P over delta T, the conservation of momentum, and then our rotational kinematics and torques in rotation. Okay? Others? Don't forget you'll have a spring problem too, I think just one. I have some of these. Collision. Huh?
There's 3 or 4.
There's 4 free response, and each of them has 2 sub-questions,
Okay.
2 parts. So you have 8 total, just like usual.
But not 19.
19? Okay, so I'm going to write down what I know. I know my radius is 0.2 meters. I know that if the car is traveling at 10 meters per second, then the tangential velocity of the tire is also 10 meters per second. And I know that V is equal to omega times R. Check my units here, because I know I'm dealing with this. It needs to be in radians. But in fact, I'm looking for omega, so I don't have to do any unit conversions. So omega is equal to V divided by R. That's 10 over 0.2, or 50 radians per second. Checking my units here. It is in radians, and that's what it should be in. So D is the right answer. Is that all for now? I mean, till tomorrow? All right, I'm going to stop the recording.